Okay, today I'm going to show you how to solve this integral using by considering the complex plane. This integral on the complex plane and yeah, like a path integral on the complex plane will let us do this integral. So yeah, let's do that. So first I'm going to draw the complex plane so we can really sort of figure out what we're doing. So we got 2D like complex plane right here. So we got the real axis here. And we're gonna have the imaginary axis in the vertical. Okay. Alright, and then so this integral in the complex, like thinking from the complex plane, is just on the real axis. It's just the integral along this path on the real axis. This 1D line. From minus r to r as r tends to infinity. Let's draw that. So it's just the integral along the real line. This. But to sort of use our integral theorems, we're actually going to consider the integral over another path and sort of add the paths together, so we can use our integral theorems and stuff. Okay, this is meant to be a semicircle. We're gonna add this path, and we're gonna call it gamma r, and it's gonna be a semicircle of radius r. So in other words, something like this. Okay. So now that we're considering this sort of path, we can actually make use of different theorems for complex integrals and use the singularities of the function to solve the integral. Okay. So let's just write this as a complex function, f of z, z squared plus 1 plus 1 over z to the 4 plus 1. As you can see, both the numerator and the denominator are entire functions, so that means that the singularities are only going to come from when the denominator equals 0, so um, let's solve that. So when the denominator equals 0, we just got this polynomial. And that's just going to lead us to wanting to find the fourth roots of unity of -1. And they're going to be our singularities. Okay, so let's quickly find out what that's going to be. So it's going to have z to the 4th equals e pi to the pi I, right? Yeah. Plus 2k. And we're gonna fourth root both sides, so we're gonna get z equals e to the pi over 4 I plus pi over 2. Oh, I didn't write k here, sorry. K. Where k belongs to it's 4 is a unit, so 0, 1, 2, 3. Okay, like this. Okay, so let's consider k as 0. Okay, we're gonna get that equals e to the pi over I um eh, uh and then we're gonna have the complex conjugate of this as well. Um so let's just call this A, this root A, and it is equal to plus I to rationalize the denominator, by the way. And then the other unique non-complex conjugate that we're gonna get k equal to, right? Oh no, k equals 1. Get to the I on 4. I will this be, and this is gonna be minus plus I on root 2. Okay. So let's just like roughly draw this on our diagram. So we got a positive A, let's just say A is gonna be here, this is A, this is gonna be B, then we got the conjugates of those, so B at A hat. Alright, so these are the roots of unity of the denominator, which, so these are gonna be our singularities. I could try and draw a circle. Did I try and draw a circle? These are our roots of unity. And we're going to use Cauchy's integral formula. So, all right, let's look at Cauchy's integral. Basically, Cauchy's integral formula is going to tell us that integral of f dz plus r to minus r. Remember, these are limiting to infinity. I'm not going to write it. Plus the integral of our gamma r, which we defined as this semicircle, of f dz equal to 2 pi I times the sum um, of the residues. I'll just write it. So we know that there's two singularities in the path enclosed by the path, so it's going to be 2 pi I times the residue f at A plus the residue f at B. This is the thing we now want to find, and that's gonna give us a value for our integral. But first, we want to find this. So really, we have to subtract this integral from both sides. This integral, subtract it from both sides, and then we'll just be left with the thing that we actually want to find. So I'll just write that out. Okay, so we've got the integral that we are trying to find that is on the real line. It's 2 pi I times the sum of the residues A and B minus the path integral over this semicircular path that we've defined. So solving a real integral like this is only really useful when this this path integral is easier than the real integral. Because if this integral is like impossible, then you haven't really helped yourself. You just sort of overcomplicated something, and you won't be able to solve it. But in this case, this integral is perfectly fine. All right, so let's think about this integral. So on the path, so on yr, have that the modulus of z, consistent with that, right? Modulus of z is equal to r. Okay. This help us imply that the magnitude or the modulus of f of z, which would be the modulus of z squared plus 1 z to the 4 plus 1. Okay, so we're going to use the triangle inequality and the reverse triangle inequality. Maybe that's what it's called. On the numerator and the denominator. So actually, let me make it. So let me write this again. Okay, so we're going to use the two triangle inequalities to show that this is less than or equal to plus of z squared plus of z minus 1. That's the reverse triangle inequality. Okay, and then obviously we know that the modulus of z is r, so this is just equal to r squared plus 1 over to the minus 1. So we're going to use this in a second. So I'm going to go on to the next page, but actually I won't box that. Why would I do that? Okay, next page. Okay, so we're going to use the estimation lemma. And I will write in the limit this time. So the estimation lemma is going to tell us that the absolute value of integral. This is the estimation lemma. It tells us that the modulus of the integral is less than or equal to the modulus of the maximum value of the function, which we just said was r squared because this is greater than or equal to the modulus of the function. We can use this as this doesn't break anything. Times the length of the path, which is a semicircle, so the length of the path is just pi pi r. Because it's a semicircle, like the circumference is just like pi times the diameter, so the circumference of the semicircle is just pi r. And then if we take this limit, we're just gonna get this is equal to 0, clearly. This limit is equal to 0. And this integral is less than or equal to 0, so we've therefore this integral don't need this modulus sign. Must be equal to 0. Okay, so that's pretty big because that means we can just like get rid of this term in the original integral sort of formulation. Okay, so now we just have that z equal to I times residue f a plus the residue of f b. So all we have left to find, or yeah, all we have left to find is these two residues, and then we are done. So is there a way to pause this? God. Okay, well, no, I guess I'm just gonna have to keep going. Sorry, this is a bit scuffed. Okay. So to find the residue, so let's just get on with it. So the residue of A is nothing but limit Z goes to A of Z A times F Z. Okay. That's where this is gonna get a little bit kind of messy. We're just gonna have to do some algebra, I guess. Guess I should do. Okay. Let's write. So we have Z minus A times F of Z, which is Z squared plus 1 divided by, which write this as the root, so Z minus A. Z minus conjugate of A is B. Z minus B conjugate A. These are going to cancel out, of course, to include the limit. Okay, so from here, I don't think I should go through this because it's literally, actually I'll go through the first one and then I won't do it for the residue of B. So we're basically subbing in A. Calculator can do like complex numbers, then it could probably just do this for you. Remember, A and B are complex numbers that we found quite ages ago. So they're like they're actual complex numbers. So yeah, that's just let me just put this in my calculator. If your calculator can't do it, just go through it. It's nothing crazy. And then literally just do the exact same thing, but the limit as Z tends to be of Z minus B F of Z. That's going to get you the residue of F at B, and you're going to get that it's literally the exact same thing. Okay, nice. Alright, so finally, integral so F of Z these is equal to 2 pi I times the sum of these, which is just going to be 2 I 2 root 2 straight. This can just which 2 should I cancel it with? Okay, pi okay, brain lag, brain lag, brain lag, brain lag, brain lag. Alright, I'm brain lagging. Let me just write this out. 2 pi I times I 2. This is just gonna I times 1, that's just 1. The I is just like disappear. 2. And then you can just rationalize this, which is gonna give like pi root 2. Oh, alright, let's do the grand finale here. So, to conclude, we have discovered that the integral minus infinity to infinity on the real line of x squared plus 1 over x to the 4 plus 1 dx equals pi root 2. That was just amazing. Wow. Thanks for watching. Yeah.